All right. So let's get going. So today we're going to review all the materials. I mean, most of the materials covered for your midterm 2. Basically, we're going to cover some parts of what we learned during the second half of the semester, and we're going to go over some exercise questions and try to answer them. So last session we learned about protection and security, and we learned a little bit about the cryptography, symmetric and asymmetric key distribution, obtaining public key and private key. And then we talked about the program threats, Trojan horse, trapdoor, logic bomb, and all the other, kind of threats that we talked about. All right. And again, PA3, don't forget that is due this Friday. I think everyone has at least one grace day, so that's fine. But use the OS Fridays still, show up on Friday and work on that. Homework is due today, so if you have brought it, hand it to me at the end of the lecture. And get ready for your exam. All right. So today we're going to talk about a little bit about logistics and cover the topics and go over the exercise questions. All right. So Thursday, May 9th, right here in class. Show up early. Again, we'll have like some seat assignments, distribution of the paper, and if we want to have a little bit of more time for midterm 2 compared to your midterm 1, then everyone should be seated, beforehand. So try to show up earlier, and so we can actually start the exam on time. So let's go over the topics that we covered in the second half of the semester. We talked about main memory and virtual memory, mass storage, file systems, I/O, protection, security, and distributed systems. Right? Some topics more were covered, some topics less. All right. So in main memory, we learned about the contiguous allocation of memory and segmentation, paging, dynamic allocation of memory. We learned about like internal and external fragmentation. We learned what is address binding and what is the translation between address spaces. And in virtual memory, we learned what is the demand paging, how we can use disk to increase the capacity of, the degree of multi-programming. And we learned about what happens during a page fault, what is like paging in, what is paging out, swapping. And we talked about replacing of the pages and the algorithms, FIFO, LRU, clock algorithm or second hand, LFU, MFU, optimal Bellotti, or Bellotti. And also we learned how to calculate the performance of demand paging. What is the page fault ratio? What is the average, dirty bit rate of different pages, and so on. Okay. So then in mass storage, we learned how the disk mechanism actually works. And then we learned about how these scheduling algorithms work. First come, first serve, shortest seek time first, scan, look, C-scan, and C-look, and the differences between them. Make sure you know them. They were like, I think in lecture 18, 19. And then we learned about reliability and RAID architectures. We learned about like RAID from levels from 0 to 6. And then we learned about 0, 1, and 1, 0. So then we covered file systems. File systems where we learned what is an inode, how a directory is structured in the system, what is the relationship between actually where does the name of a file or directory is stored. It's not in itself, it's in the directory of the parent. And then we learned about the file allocation methods on the disk, contiguous, linked, indexed, the free disk management as well, free space management with the bit vector, linked list, grouping, counting, and those algorithms. All right. Then we talked briefly about I/O systems. What is an I/O bus and what is an I/O controller? The port registers of the I/Os, how we actually interact with the I/O through polling or interrupt, and how direct memory access works. We didn't, dig into the details of them, but we got an idea of how they work. Then in chapter 14 and 15 about protection and security, last week we learned again protection, the threats, cryptography, and the methods and categories of the security violation. Right. Any questions in any of these? Last week, we also talked about distributed systems. We learned about the event ordering that happened before relationship between the events, within processes or between the processes. Then we learned about mutual exclusion, distributed mutual exclusion. We had like centralized, fully distributed, and token approaches to satisfy the mutual exclusion. Then we also learned about distributed election of the coordinator, and we learned the Bully algorithm and the ring algorithm for selecting of the election or the coordinator. Then so last session we talked about the distributed election, the prevention and detection of the deadlocks using either resource ordering or time stamping with wait and die and wound and wait. And also we talked about the centralized and fully distributed approaches for detecting a deadlock. All right. So I think if you have any questions on any of the topics, you can just like shoot it now before we dive into the exercise questions. No questions? All right. So you can answer, to these true or false, whatever it is. Just like jump in. It's not a lecture. It's like a review session. You have to interact with them, right? So the first question is that the first come first served disk scheduling tends to favor access to innermost, middle, or outermost, or none of the cylinders of the disk. Which one? None. First come first serve is actually fair. That is in the sense that it actually doesn't favor any of the where the request is, but it's just like first come first serve, right? So that's why it's not very good in terms of like efficiency, because it jumps everywhere, right? So next question: can the segments that are shared between two or more processes be swapped out of the disk? Remember that the segmentation, we could also have shared segments of the code, right, or data. So can those be swapped out to disk? Yes or no? No, why not? Okay, so we have more pointers to those segmentation, but that doesn't mean we cannot swap. Actual swapping doesn't have anything to do with locking those, right? So we can, but again, any of those, if they want to use it, we have to swap it back, right? Swap it in. So as long as any of them are using it, it's going to be, used. But again, that doesn't mean that we can't swap it, right? It's just like they're sharing it, okay? So, next, the layout of the disk blocks for a file using Unix inode is always, or sometimes, or never contiguous on disk. Sometimes. Why? Yeah. So inodes don't have to be contiguous, but if there is a contiguous space on the disk, well, the operating system can definitely use it. That's going to speed up sequential access later on, right? So it depends on, how it is, but sometimes it is contiguous, right? Next, so a piece of code which is made available to unsuspecting user that misuses its environment is called which one of these? A Trojan horse, stealth virus, logic bomb, or a trapdoor? Trojan horse, yeah. We're going over them. The Trojan horse was the one that was made available to the unsuspecting user, so this user would actually invoke it. And then stealth virus was the different type of virus. It was not available to the a suspecting user. It would actually do its job and then spread out and then go stealth, whatever. Logic bomb was when it was specifically in the program to do some damage or after some time. Again, that doesn't have to do with it being available to the unsuspecting user. And the trapdoor also was basically part of the program developed by the programmer themselves, which was a kind of a vulnerability. All right. Next, the modified or dirty bit is used for the purpose of implementing FIFO page replacement algorithm to reduce the average time required to service page faults, dynamic allocation of memory used by one process to another, and all of the above. Someone over there. I'm trying to make it. Which one? Okay. As she said, it is to reduce the average time required to service page faults, right? So try to make sure that sometimes some of the answers might seem a little bit, so maybe this helps, this as well, right? But the best choice, you always pick those, right? Because again, the chances are you'll have like MCQ questions on Thursdays. I mean, not as many, but still. So if you have any doubts, pick the best one. Don't pick 2 or whatever. All right. So question number 6. In terms of reliability and performance, compare bit vector implementation of free block list with keeping a list of free blocks where the first few bytes of each free block provide the logical sector number for the next one. So one is bit vector that you want to compare, and the other one is list of free blocks where each block points to the next one. Which implementation is that? Linked one, right? It's linked. Each block links to the next one, so that's the linked one. So what is the comparison between the bit vector and the linked list? Go ahead. Yes. Mm-hmm.
But like for the bit vector one, you can just like you have like the areas.
Yes. So that is for performance. How about reliability? You go ahead.
For bit vector, if you lose a node, then you can still access the other node with the availability. For the linked list, if you lose one node, every other node after it is what's there.
Right. So if you remember, first of all, we'll go over this. The free list head and then all the links and were like that, and the bit vector was a bitmap of all the available free blocks. So the performance-wise, it is actually difficult in order to find for example, contiguous free blocks, because you have to like traverse all the way and then find if they are like contiguous. Whereas if you have the bitmap loaded into the memory, it's actually very, very fast. You don't have to access disk blocks at all. And the bitmap itself is like tiny, so you can easily bring it to the memory. And in terms of reliability, if one of the blocks is corrupted, then the link to the next free blocks is just gone. It's difficult to retrieve those back. But in terms of like the bitmap, if one of these get corrupted, well, it doesn't matter because you have them here in the bitmap. And where you store the bitmap itself, if you want to save it from corruption, you can actually multiply, because it's again tiny. You can have multiple copies of it for reliability on the disk, and then then it will be fine. You don't actually lose anything. Yeah.
For the grouping number 16,
Huh?
has the last one as a -1?
Yes.
Does that just happen for just after the last one, or is that just to complete a group of 3?
No, to complete a group of 3, you actually point to the next one. So here, for example, you see here we have like 7, and 7 points to the 8. The next 3 blocks are 8, 9, and 12, right? So basically, it has the 8, 9, and 12, and then the next group will be already in the last one, which is the 12. But when all the 3 blocks are done, this is the last one, then you have a -1.
What if 18 wasn't being used in this case, and so we had for 16 it was just 17?
Okay.
We just have one -1 and the other one would be blank?
I mean, you can have 2 -1s as well. Doesn't matter, right? I mean, because again, for grouping, you're still kind of traversing, but you don't actually access each and every free block. Rather, you actually access a group of them, right? So once you access this 16, you're gonna like traverse for the free blocks, and then either when the first -1 or all the -1s are just like end of them. Yeah.
So kind of what indicates the end of?
Come on. Come again.
What indicates the end of the whole?
The -1, yeah, it's basically the terminator of the end one, the last one. It indicates that there's nothing from here on. Okay? So, yep, this is what we discussed about the performance and reliability of the bit vector compared to the free list, okay, or the linked list. So, next question, memory and paging. So, consider the paging table on the right, and what are the physical addresses of the following logical addresses of the page and offset and the words on them. If, by the way, for any of the questions it's not clear, or you feel that we're just like passing or skipping too fast, just let me know and we kind of pause. We don't want to just skim over the slides. You'll have all the slides, right? But we want to actually see and understand how they're solved, right? So a page table, you remember, it was like reside in the memory itself, but it would actually help us to find where on the physical memory each page is, right? And there was like the address was like a bundle, and it was split, and then into a page number and the offset. So now that we have the paging here, the page size is 4 because each page is like 4 address apart. And now the page table itself, we have like page 0, page 1, and page 2, and page 3. So this is the logical memory. We have 4 pages from 0 to 3. And now we have like frames here. And in this case, we have actually more frames than the page table here. But that's usually not the case. And here, we didn't actually, for example, cover the whole logical memory. The logical memory is like obviously larger than this. But we're just like covering these 4 pages because these are what we care about, right? So in the page table, we see, okay, page 0 is like mapped to 5, which is frame 5, 0, 1, 2, 3, 4, 5. Here is page 0. And then page 1 is mapped to frame 6, which is here. Page 2 is mapped to frame 1, which is here. And then page 3 is mapped to frame 2. Okay? Now, considering the offset is from 0 to 3, that means like if you take the addressing, what is the number of bits for the offset? If the page offsets can be 0, 1, 2, or 3, what is the number of bits for the page offset? 2 bits, right? You have like only 4. So, and then the rest of the address bit would be for page index. When in this case, we're only going to like use again 2 bits, but it can be definitely larger, right? So page 0 address offset 0. Where is that? So you're going to like look at the page table. So this is what you're actually going to do like the CPU, right? So page 0 offset 0. The page 0 part, we're going to go take a look at the page table. Page 0 is mapped to frame 5, and then you just like going to jump to frame 5, 0, 1, 2, 3, 4, 5, and then from here. Offset is also 0. So 20 plus offset 0. That's just right there. Address 20 and the word is also A. Alright? 1 and 4. Where is that? Come again? H. Why is it H? So page number 1, we're going to take a look at this frame 6. So it's here. What about the offset? So 24 plus 4. It's not actually in the page. Actually, in this case, it's not even like it's not even like feasible or like you cannot actually address this because again, you have only 2 bits for page offset, and 2 bits cannot be 4. So this is just plain wrong. Right? It's not that you are exceeding a page. You cannot exceed a page. I think James is he here? He asked this on Piazza. So in paging, right, you cannot actually access out of the page. It's just like either 0, 1, or 2, or 3. If you actually increment that bit, well, you will change the index, right? So it's just like not possible. So page 2 and offset 3. So 0, 1, 2. This is, where is it located? On frame 1, so 0, 1. So it starts from offset, the physical address of 4, and you add the offset of 3 to 4, and you get 7. And that will be K. Alright? Well, sorry. 7 is like this. K is 6. L. Alright? Got it? If you have any question in paging or translation, now's the time. So now next question will be the segmentation. So this is different than paging because in paging, as we just saw, you have the fixed number of bits for page offset and you cannot exceed that. But in segmentation, that's not the case. The segmentation, the segments can have like a smaller limit than what the segment number, or like the number of bits for offset allows, right? So in this case, for example, we say consider the following segment table. 0, 1, 2, 3, 4. We have 5 segments, and we have a base address for each of these segments, and we have a length for each of them. Now, as we have the length of up to 600 bits, right? 600 address. So the number of bits for the segment offset is at least 9 bits, or 10 bits actually, right? So consider that we have 10 bits, so that means if you have like 32 bits of addressing, 22 bits can address your segment number, and then 10 bits can address the offset within the segment, which can change from 0 all the way to 1023. Okay? So it can change. You can address an offset up to 1023. But if the length of this segment is only 600, you can technically address the offset of 800. But it's just like wrong. You cannot do that because it exceeds the limits of that segment. So this time is not that like you cannot put that into the numbers or the digits. It's just like that how you map it. So let's take a look. So take a look at this. Segment number 1 offset 100. Again, you take a look at the segment table here. So segment number 1 starts the base address from 2300. That's fine. We have found it. And then what about the offset? So we can add the offset to this and get the 2400. But it's just like that. It is not legal because this segment is only 14 bytes long. So, addressing that will probably address something else. It might even be paged. Not paged, actually available. There's something there in memory, but it might actually be in a different segment. So it might be for a different program, whatever. So this is just like it's not legal. How about this one? Segment number 2 offset 0. So segment number 2 starts at 90 and 0 is just like the base itself, right? So it will be actually 90 itself. The last one, again, is the tricky one. So you have just to know that, when the segment length is 580, the offset that is allowed is from 0 to 579. So this is, again, wrong because it exceeds the limit. All right? Any question in this part or segmentation? No?
So in here, special table to storage this segment table to base map length. There are two storage devices or something like a page
Well,
table.
segment table is similar to page table. It is also, you have to set it up, the operating system has to set it up, and like the CPU should have its segment registers, base and length, or limit, and when the operating system does a context switch and loads a process, the instruction pointer, a stack, whatever, when it set it up, it also takes the information out of the process control block, which is related to the base and length of the segment table, into the registers of the CPU. And then when the CPU starts running the instructions, it has access to this table. Now, where is this table? Again, it resides somewhere in memory in the kernel space, and so it doesn't go away with when the processes changes.
So is there any internal fragmentation or external fragmentation in the segment?
When you have segmentation, you don't have internal fragmentation because the segments that are being assigned to the processes are the size that they actually are asking for. How about the external fragmentation? External fragmentation. You can also avoid external fragmentation if operating system loads them. Usually, still the segments are aligned in terms of like some of the bits. So I think like in x86 architecture, you have the segments shifted 4 bits. So always the segments start at an address which is divisible by 16. So you won't have this address as a base of the segment or this one. Some of these are just like physical optimization. Some of them are just like the architecture, how it is designed. So the address space was designed to be like in some way. Yeah, so the fragmentation is different. So you might still have some fragmentation, but it would probably be less than like paging. All right? You have a question or no? Okay, no. So next one, demand paging. Okay, so we might dive into the blackboard a little bit just to see. So we have the CPU utilization like 18%. So the CPU seems to be not very utilized. Paging disk is 96%. So the other I/O devices are 6%. So what does the system look like? It looks like it's thrashing, right? Because it's just like paging all the time and not useful work is, happening a lot there, right? So, and it's trying to ask like, what is in this situation, what can help the system? So, does install a faster CPU help the system? No. Why? Yes.
You're increasing the CPU speed, but then you'll make more paging happen, which doesn't help the paging.
Right. The CPU speed is not a problem here. Where the bottleneck is now the paging disk. So if you increase the CPU, either you just like actually decrease the utilization because the capacity is larger, or if you want to keep the same utilization, that means you're increasing the degree of multi-programming, and then actually increases and makes things worse. Right? So how about a bigger paging disk? If you install a larger paging disk, does that help? No. Why? Yeah.
The size of the paging disk does not affect the amount of memory that is needed to increase the page fault.
Yes. Exactly. I hope you can write it exactly like that on the exam as well. Thanks. So, the paging disk, remember, it's the hard disk, which is not the case of the problem right now. It's the space is large, and it's like it's supposed to back up the memory, and like increasing more is just like it's not going to help. The problem of the page fault is with the physical memory. That's why you're keeping swapping in and out, because the physical memory is limited, not the paging disk, right? So how about decrease the degree of multiprogramming? Yes, because the problem is because we have like too many processes. When we want to like context switch, we don't have the pages available, so we have to swap in and out. If you decrease the degree of multiprogramming, then we actually suspend some of the processes, wait for the other ones who are now available on physical memory to finish up, and then release resources, free up memory, and then we can continue with the other ones, right? How about installing more main memory? Or physical memory, main memory, physical memory, RAM, these are all, kind of. Yes, because again, the problem of the page faults was for the limitation of the physical memory, and now we are, by increasing that, most likely you're going to help the situation, and the reason that we don't say always is with the algorithms, it's most likely. Yes. So, it's most likely again, and we don't say always because we have seen in cases, for example, that the Bellari anomaly can happen when you increase the physical memory, you actually make things worse. Again, it's not, common, and it depends. Like if you double or like triple the size of the memory, most probably again, you're not going to have, suffer from the Bellari's anomaly, right? So, it is likely, not most likely. Alright. So, now get to a little bit of a calculation. So, demand paging. You won't need any calculator, by the way, in the exam. Simple calculations you should be able to do on paper or your hand. If you have to do a division, yes, that's not needed in the exam. But, subtraction, division by 1,000, yes.
Will we be required to do a number of formulas?
What's that?
Will we be required to do a number of formulas?
What do you mean?
Like the estimated access time?
Yeah, these are all the things that should be covered. But you should be able to calculate them with hand if they're in the exam, yes.
Can we use a calculator?
No.
So we can't speed it up.
I know, but it's just like makes things easier because, we want to avoid things. But you can use pencils. Yes.
So will the encryption questions not be asked then?
What's that?
Will the encryption questions not be asked?
Encryption questions can be in the exam. You should be able to obtain a key. Because for like the small numbers such as like, prime numbers up to 100, you don't need anything besides just like checking a couple of numbers, right? And, so obtaining a key is fine. But you're not required to like, take a number and take it to the power of 31. No. Right? So, but, the steps that are needed, how the key was obtained, what should be like, primed relative to what, these are just like things, that you need to know. Alright? So, let's get into this question. a paging system where 40% of the page table is stored in the registers and the rest needs to be addressed from the memory. Again, these numbers obviously can change. Some of these exercise questions are taken from previous lectures just to make sure that, again, they are covered. But some of them, can just, obviously vary the numbers, right? So we're saying that 40% of the page table is stored in the registers, meaning we have the TLB, and 40% of the time we have a cache hit. Okay? And assume any reference to the memory takes 100 nanoseconds, and 20% of the time the page that is being replaced, that doesn't have to do with caching. This is the demand virtual paging. So if a page is not available on memory, 20% of the time we have to definitely swap in, but also at 20% of the time it's dirty and we have to swap out. And we are told that swapping page in takes 1,000 microseconds or 1 millisecond, and swapping out of the page out to the disk is 2 milliseconds, right? And now the first question is, how long does a page memory reference take? So first of all, the question is, how long does a page memory reference take? So we're not dealing with swapping here. We're just assuming we're dealing with memory. Okay. So when we're dealing with a reference page, it means, accessing some data which is available in the page table. Now, we have been told here that we have the page table cached into the registers, and 40% of the time we have the cache hit. So first thing first, you have to get the effective access time to the page. This one. All right. So what do we have? So %40 hit, cache hit. All right. And probably you don't have to write, because the answer will be on the next slide, but it's just how we're going to again. If you want to write, obviously go ahead. So, first, and then it was 100 nanosecond, right? So, we have seen there are a couple of ways to do the calculations. We're going to cover both. It's up to you how you would like to go. So when you have a cache miss and cache hit, the effective access time of memory, right, in this case, is the probability of a hit multiply hit time plus the probability of a miss multiply miss time. This is way number one, right? And the probability of a hit, it has been told us it's 40%. 40% is a hit, right? Not the miss, yeah. So it's 40%. And the hit time is where you only need one access to the memory, because when you have a hit, that means your page, that part of the page table is in the cache, so it's immediately accessed, so you don't have to access memory for that. But then now you have the frame number, and then you can access the memory and, access your data. So that is 100 nanosecond, or in this case, we're going to just go to microsecond, 0.1 microsecond. So hit time is, you have the page table, some part of that page table is in the registers. And registers, compared to access time to the memory, are immediate, right? They're much, much faster, orders of magnitude, right? So if a page table, if an address is paged and it is in the cache, that means if I want to address the page table to access to the frame, to get the data, first I check in my TLB. And if it's a hit, which is the 40% of the time, I don't need to refer to the page table anymore. I directly have the frame number, right? So I get it from the cache immediately, and then I access the frame, right? Now, a miss rate is basically the rest of the time, which is 60% of the time. And that is, I'll check in the TLB to get the page number, but I don't have it in my cache. So that means that in order to find the frame number, I have to access the page table itself, which is in memory, and then I will have the frame number. Now that I have the frame number, I add the offset, and now I can access the physical memory again. So in this case, I have two memory accesses, right? So the miss time in this case, it's not the miss time, it's the time that it takes in case of a cache miss, right? So I just wrote it like that. So you can actually, time of a miss, and then it can have it like time of a hit. Right? So you have 2 times of the memory reference, which is 0.2 microsecond. And in this case, we have 40% of the time, and that is 20 nano. So if I want to get to access the data which is on some memory, I have to get the frame number, and in order to get that frame number, I have to access the page table itself, right, to translate the page to frame, right? So I'm going to get a little bit of help here. What? 160 it is basically, yeah. Nanosecond or 0.16 microsecond, right? So this is, you have a question? So 0.2 is double of this. 0.1 is 100 nanosecond of memory access time, which is 1 microsecond. It's been in the question.
Are we multiplying 0.1 by 2 for the 2000?
Come again?
Are we multiplying the 0.1 by the 2000 microseconds?
No. At this stage, we're not doing any swapping. At this point, we consider the page to be in the page table already, so we don't have the page fault. This is just an effective access time of memory itself. Wherever in memory that you want to access, if it is paged, then you have to deal with this. Now, if it's not paged, that means even when you access the page table or your TLB, you realize that it is not available in the page table. All right? So this is just an effective access time of memory. Now, let's see. Next part. The other way. I wanted to also calculate that. So the other way, actually, which is, I find it a little bit easier, but again, if you find it easier this way, it's up to you, is to separate what you already have to do and the extra time that you have to put in some cases, right? So in order to calculate this, you can also say that effective access time of memory access is that, well, obviously, in order to access some data in memory, you have to access memory one time, right? That's just like there, right? So you have one access memory, which is always there. And in some cases that you cannot access it directly because it's not in your TLB. You cannot translate that page to a frame immediately. So what are the chances that happen in the miss rate? So you have to calculate actually I will write it, the time of a miss. Basically, probability of a miss, multiply the extra overhead. Not the whole time in the case, but just like extra overhead. Right? So memory access we've been given that is like 0.1 microseconds. And the ratio of a miss of your cache is 60%. And an extra overhead is another access to the memory in order to get the page table, right? So the overhead itself is just like one more memory access, which is like 0.1. So this usually comes out a little bit like easier. So, this is like 0.06 and this is 0.1 and the answer would be 0.16. Right? So, this is what we just covered. Again, either you have the hit time and the miss time, or you have the always time and the extra time. It's up to you. All right. So the next question now deals with the paging. Now it says what is the effective access time if the page fault ratio is 1 out of 1,000? That means, up to now we just covered the access of the memory, and we assume that wherever that we want to access, our logical address is already in memory. That means either we have access it directly through the TLB, or we just look up at the page table and then we find it on memory, right? Now, overall, it says that, okay, we have page fault ratio of 1,000. That means out of every 1,000 pages that we try to access, one of them is not in memory. It's not just like there. So in those cases, we have to actually take a look at the hard disk, swap in some pages, right? And now it also, in some of the cases, we have to find a replacement, and 20% of the time, we have to also swap out a page, right? To make some space for that page. Okay? So this is the effective access time of demand paging, and it's asking what is it in the case of a page fault ratio, right? So let's take a look at how we deal with these. In order to save time, I'm bringing this down. So in order to get the effective access time, again, there are two ways to do so, right? One way is to deal with the time that it takes that it is there, the time that it is not, right? So the effective access time is that probability of a page table, like if wherever you want to access, it's either in the memory or not. Chances that it is paged multiplied by the time that it takes for a page table plus chances that it's not paged or swapped multiply the time that it takes to page in and read. Right? So now each of them might not be very, straightforward. So we're just going to go over it again. I prefer the second method. It seems easier for me, right? So we already covered this part. It has been told that what is the percentage of the time is just paged, right? It is what? It says like the false ratio is 1 out of 1,000. That means 1 out of 1,000 time it is not paged. So this is being given to us, and consequently this has been given to us. Right? You can also basically, instead of like multiplying 999, just write 1 minus 1,000. It makes things easier. Now, the time that a page is like paged into the memory, we already calculated. If address that we want to access, it's already paged in the memory, we just calculated and it was like 0.16 microseconds. Right? How about page in and read? So in case that a page that we want to access, the memory address that we want to access, it is not paged. So first of all, it will take some time for us to realize that it is not paged. Right? That can be either checking the TLB and then checking the page table. So we have to first access the page table to realize that it is not there. So these numbers usually we ignore. The smaller numbers in this case is ignored because we're dealing with the disk. The memories are ignored. So what is the time that we have to take a page in? So in order to take a page in, sometimes you have to swap out, sometimes we don't have to swap out. Itself has something in it. So we have the probability of a dirty page. So if the frame that we want to evict is dirty, then we have to multiply that by swap out and in. In some cases, if the page that we want to evict is not dirty, then the time is just to swap in. Right? Because we can just drop that frame. It's not dirty. We're just going to drop it, and then we're just going to swap in. Right? So let's see what are these numbers. So it has been told to us that 20% of the time the page is dirty. Right? So this is 20%. Swap in and out. One is 1,000. The other one is 2,000. So the time to do both is 3,000. And if the page is not dirty, that's just like a 1 minus this, which is actually I can just like write it again. 1 minus 2%. Swap in is just like 1,000. Okay? So in this case, if you want to sum up, I don't have any other color for Chuck. It might help.
Will the numbers be easier than this?
I think if you take the second method, it would be easier. The numbers usually are just like these. Like you still have to do one multiplication or something, but if you do this a couple of times, you actually find the steps. It's usually just easy. This number multiplied by this number is just like you find your rate, and you will have enough time. Yeah.
Can we leave it like?
No, this is not enough. This is not enough, right? The third part, I'm going to say where you can leave, right?
It takes a lot of time, though.
Yeah, but again, you'll have enough time. But you're not also explaining it loud, right? It's just much faster, right?
Can you give us the formats?
So, no. I have given it in the slides, right? It's just so, let's see. 1,000, you can just multiply this into this and it will be easier, right? So, this is, 1 second, plus, so in this case, it's just this 1,000 goes with this 1,000, and that's 60 out of 100. And the next is, again, this 1,000 goes with that, and then you'll be left with 80 out of 100. And these are just all together, 140 out of 100, which is 1.4. And this is already going to go away, so this is a small, so you can add this plus that. So 1.4, this is 0.16. You add them up to 0.56. 1.56. Then this is microsecond. In this example, I didn't even look at the solution. The solution is next page. Right.
What does that say? So you have 1 over 1,000 times P something times T something plus, I don't know what that says.
This one?
Yeah, just all. I can see last one yellow.
Okay, so, alright. Get the idea, and then you can take a look at the lectures, and then you also realize, right? So the idea is that if the address that we want to try to access is not paged, right? So we have to access the memory, obviously, right? And that usually cancels out with this, and it's really tiny. But we have to swap in and swap out, right? And the consideration is that, okay, when we want to swap in, we also have to evict a page, right? To make some space. Now, the page that we want to evict, do we have to swap it out or not? That is the chance of the dirty bit, right? Now here we have been told there is a chance that the page that we're trying to evict is dirty, in which case the time that it takes for the whole process is to swap out and swap in. So this is that part. And the chance that the page is not dirty, which is, the 1 minus that one, then we don't have to swap out. We can just drop that frame immediately and then just swap in the next page. So this is the time that is calculated. Right? Go ahead.
Were you just saying that because the memory access, for the right-hand side, that the memory access association is ignored?
Yeah, I mean, if you even put it, basically that will just cancel out with this one.
Do we need to write that on the exam, or does this assume that?
It's fine. Yeah, it's fine. So the second one, I think it's easier both to calculate and understand. So I'm just going to remove this part and just go over that. Alright? Okay. I'm actually going to just go over this slide because I don't want to waste time on this. Okay? I really don't want to rush into the rest of the slides. Okay. So this is the first method that I was saying, right? Average hit rate plus average miss rate. The average hit rate, this is the hit rate of pages, right? So we already covered this. Now, this part also you can break it into the always part and the extra time, okay? So the next method, the second method, does both of them. So you always have the always part and then the extra part. Let me finish this and then if it didn't answer, right? So, we always have to access memory anyways, right? Whether it is page or it's not. So we always have to access one memory time. That's there. In some cases where the page is fault, meaning where we're trying to access is not in memory, then after, where we've tried to access it, either in the TLB or the page, the table, it doesn't matter, we have to do something. And we have to swap in. Now again, this is average swapping overhead. Now, again, in the case of this fault, page fault, we always have to swap in. In some cases, we also have to swap out. Break it like that, and again, it will become easier. So, we always have to access memory. We already calculated it in the first part. In the case of a page fault, we already have to swap in, which takes 1,000 microseconds. In some cases, which the evicted page or frame is dirty, we also have to swap that out, which takes another extra 2,000 microseconds. Alright? So if you calculate it like that, you can see the numbers are just like much less. It's just easier. You just like multiply 0.2 by 2,000 and you get like 400, and then get like a 1,400 of it this, and the page fault is now here. You multiply like 1 out of 1,000 into that, you get 1.4, you add it up. Like this calculation is really not that long, or you don't need anything for this. The idea behind this is like this, but when we move around with these numbers, basically it's easy when it's like that. So now go ahead.
I think it will take a minimum of 10 minutes.
Yeah, around so. Yeah. Usually it's easier to do put the numbers at the last point, because a lot of times these are just canceling each other, or things are becoming easier. 10 minutes is, I would say, like high. Like 1 minute to read, or 2 minutes to read, and like 5 minutes to solve. 1 or 2 minutes to check. Yes.
How many points would we get if we leave it at the unsimplified equation?
Oh, come on. You're losing the other slides. Come on, let's go. So, what should be the maximum acceptable page fault ratio if we only want 50% degradation? So this is the other case. What is the degradation? That means if we are using demand paging, we are losing some time, right, because of the paging. Now, we say, what is the degradation? The degradation is the ratio of the effective access time that we just calculated over a normal paged direct memory access. Right? So we calculated that this number up to here. Here, you need that because you want to change the speed. So this is the effective access time. This plus this. What is the direct memory access time? This one. So if you divide this by this, you get always something greater than 1. Right? You get 1 plus this divided by this number. And now there you can calculate what it is that you want, right? So when you get this one, this is this is the formula that you want, right? Just memorize this. So the degradation is like that. The effective access time divided by the memory access time, and then you want it to be less than 150%, right? So now you just calculate the numbers. The effective access time, we got it. The memory access time, we got it, and you want it to be less than 1.5, right? And you just do a little bit of a moving of the numbers here and there, and you multiply both by this number, you get to 0.240, and then you move this number over there, you get 0.80, and then you want your page fault ratio to be less than that. At this point, yes, you can leave it as that. You're not required to divide a number by 1400. But multiplying 160 by 1.5, come on, it's not that, right? So, but yes, some of the times, so this basically combines the understanding of the topic of the virtual memory and a little bit of your focus to make sure that you do the calculations right. Some of the questions are not necessarily doing any calculations. Some of them are just like that. So, there it is. All right. So this is how you basically calculate the degradation. You have the effective access time divided by memory access time, and you have the percentage. Yes.
What about those calculators that solar power?
No. If you have something like this in the exam, you'll have enough time for it. Don't worry.
That's smart, man.
Well, after we get the equation, isn't it not an OS problem anymore? It's just a math problem.
It is. Okay. If this calculation is really going to be difficult, I'm going to be okay with a 4 operation calculator, right? But if you don't have it, don't come up with your phone and say, yeah, I don't have a calculator, I have to use this.
Is this good enough?
Does it is it programmable?
I don't think so.
Okay.
What about this?
That's fine.
Yeah, hey, it's scientific.
That's scientific, dude. I did QBasic on those. Yes.
What about a Raspberry Pi?
A what?
Raspberry Pi.
You can have no, not Raspberry Pi. Like calculator is like fine, but again, I'm just like saying that you don't need it. You can bring them in the for the exam, not the phones. Please don't use any phones. And one of the reasons that I say like the calculator is not there is just because so you don't. I mean, it's difficult to see if that is a phone or a calculator. You know, we want to avoid it. So bring a calculator if it is one of the questions. If it's not one of the questions, then we ask everyone not to bring it out, right? Because I can't tell if this is on the exam or not, right? I cannot tell that. But bring the calculator. If it is on the exam, you can use it. If it's not on the exam, well, obviously phones and calculators are away. Yes.
I was just going to ask if we bring an abacus.
What's that?
Bring a calculator, never mind.
What?
So we can bring a calculator in the exam?
Yes. Yes. So you can. Okay, everyone? You can. Let's move on. We have more questions. So consider virtual memory system with 34-bit addresses. And the first 23 bits are used as a page number, and the last 11 bits are the offsets, right? So remember, this is also given like, hint here. So always 2 to the power of 10 is a kilo, so that one makes 2 to the power of 20 a meg. And so it says like out of the 34 bits, the first 23 bits is the page index or number, and then the 11 bits is the offset. So it's asking how many words does a single page frame have? Huh? 512. All right. So the way, okay, I see. He just gave it the direct axis. When we have the offsets can be from 0 all the way to 2 to the power of 11, negative 1, right? From 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, numbers will be 11. So that's 2 to the power of 11, right? So that's like within a page or a frame. So that's 2 to the power of 48. How did you get like 5? Why did you get 9? Oh, you just like miscalculated. That's right. So this has been given to you. That's why. All right. So that's 2K. The frame size here is 2K. So and if we assume, that's a typo. If we assume each word is a byte, then that's like 2 to the power of 11 bytes. Because here, if you see, it says like how many words. In memory accessing, you have something like the address space, which is like the index or address that you put on the bus. And then based on the size of each word is what you get. So if you give it one address and the address, like each word size is one byte, that means you give an address, you get a byte. You give an address, you get a byte. And that's the size of the memory is the number of indexes or addressable memory multiplied by 1 byte, which is in this case. In some cases, that's not what it is. You give an address, you don't get 1 byte, you get 2 bytes. That's because the word size is 2 bytes. You cannot directly access this byte. You have to access 2 of them and get 2 of them. But the benefit is that now you have double your capacity of storage, because with the same number of bits, the same number of indexes, for each of them you get 2 bytes. So now the total number of bytes that you can store in this memory is double than this. The number of words is going to be the same, but because each word is 2 bytes, now you have like 4 kilobytes of space. But they are not like byte addressable. They are word addressable. Right? So this is something. You might have like words with microcontrollers and some of them are bit accessible. That means you can directly access or modify 1 bit of them. Usually that's not very efficient because you have to like waste a lot of memory to access 1 bit. So sometimes they only have part of their memory bit accessible. So this is the case. So a lot of the times you can make a storage is larger. So if you like give an access to 1 memory block, the memory block actually gives you, 4 bytes of, each word is like 4 bytes. Alright? So next part of the question. Assuming there are 2 to the power of 10 frames in the physical memory, how many bits are needed to address the physical memory? So we have been already told that the logical address space is 34 bits. But that's usually not the case with the physical memory. Physical memory is not 34 bit. That's a lot of physical memory, right? But instead here we were told that's like what? 4. That's like 16 gigabytes. It's not like compared to your laptop, it's not a lot, but compared to the 32-bit address space and the older ones, it's a lot. So and in this case, we are told that the physical memory has 2 to the power of 10 frames. What was the size of each frame? We just like calculated 2048 bytes, or we just like it's easier to just do with the number of bits. So 2 to the power of 11 bits, right? So if we have 2 to the power of 10 frames, and each frame is 2 to the power of 11 bytes, that means the whole physical memory is 2 to the power of 21 bytes. That's like 2 megabytes. That's not a lot, but that, comparing to your Pintos, that's what you get, right? And then if your physical memory is like that, then obviously you only need 21 bits to access it. Your architecture, whatever physical hardware can be like that. Alright? So the next part is assuming a single level paging and each page table entry to be 4 bytes, how many megabytes of memory is needed to store the page table? So you remember the page table, and the simple case was a direct page table. So we have one page, we have access to like the indexes and get the frames directly. What are the number of the indexes in the page table? The number of pages in your logical address space. How many were there? 23. So you have 2 to the power of 23 different pages that you can access, and that means your page table should have 2 to the power of 23 indexes. It's an array of 2 to the power of 23 size. And it says each page table entry is a pointer. It's an address of like some physical address, and it is stored in 4 bytes. That means your array is 2 to the power of 23 indexes. Each of them is 4 bytes. So you multiply these together to get the size of your page table altogether. And that is 2 to the power of 25. 20 of it is 1 megabyte. 2 to the power of 5 is 32. And you get like 32 megabytes of page table. And again, this is like right calculated after this. So your actual physical memory is only 2 megabytes, whereas your page table itself, if it's direct paging, takes 32 megabytes. So that's why you have 2-level paging. If in your Pintos you have the page directory and the page table, in 10 bits and 10 bits separate, because it's a waste of memory if you have like 32 megabytes only for page table, right? All right, moving on. A distributed system consists of 4 sites given below. You can take a look at this example. This is just like if you want to like have a calculated distributed deadlock detection, you have like do a lot of message passing. In this case, you can like use a centralized, and you don't have the PX in these the node the external node, so you cannot like pass. So instead, every one of the nodes should like have a coordinator in center. Everyone like passes their own local wait for graphs into them, and then that resolves everything. So here we have like P1 is waiting for P15, but here we have P3 is waiting for P1. They cannot see this, but the coordinator, once like they bundle all of them together, they actually figure this out, and then you realize that, oh shoot, like all of them are just like linked all together in like a gigantic like deadlock, right? So such questions, again, you should handle. Like this is like a bigger one, but if it's like a smaller scale, you should be able to like find it. All right. So next question is doing with the disk. So when you have like the disk services requests of the different tracks, this is the reference that is being given to you, the string, and then it's asking for different algorithms: shortest seek time first and C-scan. Right? You have to know what are they. The first thing that you need to do and make it easier is to sort them. Right? The first thing is to sort these requests on a disk so you can like look at it as on the track, right? 20, 60, 80, whatever. And then it has been given to you that it is now at 100, and prior to that it was at 101. So in some algorithms the prior direction is important. In some of them, it's not. So in the circular ones, it's not, because it's always servicing in increasing direction, right? So, but in scan or look, the direction actually just continues. So if it's like going from 101 to 1, it just like comes down and services all the 1. In circular ones, it doesn't. Yes. True. Okay. So, you sure? If you only...
With what you just said, you said that the circular version of those algorithms, it goes all the way to the beginning and keeps going, so it's unidirectional.
Yes.
Functional, when it's servicing.
Yeah.
So if the cylinder was at 100, or was at 101 and went to 100, that means it's not resetting?
Well, not necessarily. Maybe there was a time that it didn't have any requests, so it actually went all the way and then back, and then now it's at 100. So it's like telling you the previous request. It doesn't tell you all what it took. But in a scan, from that request to this request, it comes in this direction. In a C scan, it goes all the way, comes back, and then gets to here.
What the direction of the C scan to the right?
The C scan and C look, their direction is always the unidirectional. It's always going up. All right. So in the shortest seek time first, we are at 100. It actually doesn't matter where we were. From here, we picked the shortest one, going from 100 to 1, and then 2, and then 80, and then 60, and then 20, and then going up to all the way. And you calculate them again. So from here to here, it's just like going up. So you just like subtract this from this. Again, simple calculation. This, yeah, I guess if you bring a calculator, you might not as well use it for this. And, just like make sure you subtract the numbers correctly. This one has this many head moves. The C scan, it doesn't matter that it was like 101, but the direction always goes up. So from 100, you go to 101, all the way to 450. And because it's the scan and not look, you have to go all the way to the end of the disk, which has been told by here, the number, and then come back all to 0, and then again start servicing up. Okay? So obviously in this case, shortest seek time first is more efficient because it doesn't waste time, right? But it might not be as fair depending on the situation. All right. So next one is the page reference string and frame and the clock algorithm, right? So you remember the clock algorithm? We give the second chance to the frames that we were trying to evict, but they have been referenced recently, so we change their bit to 1, and so on, right? In this case, it's just like 1 bit. It's not the 8-bit LRU. It's easier. So then the frame has been given to you. This is the solution. We're just going to go over it, like part of it quickly. There are 2 things. You're going to study this well, and if you have any come up with any question, ask it on Piazza, right? So you start with nothing. You evict your victim is like supposedly here, and then you bring page 1. 1 is not in the page table, so you bring it, and then you move your victim here. Right? And whenever you bring a page, you move the victim, and also you have to set the page reference to 0. Now, page 2 comes, again, you put it to here, and then move. 3 and 4. And then, now, at this, you look at this frames, page 5 comes, page 1 is the victim. The reference bit of page 1 is also 0. So, that means that you just bring 5 over it, replace it, and then that's it. And then 6 and all the way to here. In this case, when 5 is already in the page table, what you do is you update the reference bit to 1. 6 comes, you update that to 1. You don't move the victim anymore because you only move the victim, the colorful cell, only when you bring a page or you're looking for a victim. So when you want to now reference 2, 2 is not in the page table, so you have to bring it in. Who's your victim? 5. Is 5 0 reference bit? No. So you give it the second chance, you change it to 0, you move on to 6. How about 6? Again, it has been referenced, so you change it to 0 and move on. How about 7? 7 is the reference bit is 0, so you actually replace that and move the victim to the next one. This is the way that you should go. And preparing this, actually make sure you actually check every 4 or 5 references. So you do this here, just read and do it again. Because at this point, if you have you fill all the way and you realize that, I made a mistake here, you have to do all of it again. This happened to me when I was calculating this, right? Because I was not in an exam, right? So I was just okay, I'm just going to go over and check. But 2 times it happened, I realized I made a mistake, especially because I was copying and pasting all these numbers in Word. I was not actually writing them. So, chances are you make a mistake. But in the exam, make sure you do it 4 or 5 references in order to prevent that waste of time. All right? So, this is the best fit, first fit, and worst fit. I don't have it in the lecture. We have covered it previously. Maybe I put it on the, this is slide in the answer. Couple of minutes, please. So this question is, again, I'm not going to cover it. You go over it. If there is a question, ask it just to save us time. I made the answer clear on the slides, so it's like should be easy to find. So these are files, these are the directories, and every step that we go through of these commands, we see the result that we want in the logical view as well as the system view, what is happening, this is being moved, and also, right? Make sure you study this. And they happen before the relationship and concurrent processes is also, again, like this. Alright? So, in the last couple of minutes, I would like to everyone to listen. First, make sure you study well for the exam, show up early, and, continue with the implementation of PA3. The office hours are set for tomorrow, today. The office hours are mostly for exam. If there's no one there, obviously you can also bring your questions. Alright? And lastly, I would like to thank the TAs of this course, Vivek, Asif, and Navina. They helped us a lot. And also I would like to thank Dr. Karthik Dantu, because they provided a lot of support for me. And a special thank to Professor Tefik Kosar. A lot of my material and content and slides were adopted from their slides. And then also they helped me a lot during the course. Alright? So I hope you learned a lot during this class. And well, I guess see you everyone on Thursday during the exam. Alright? Take care. Thanks.